Okay, I'm going to go over Notebook 12, but also Lab 8 is due this weekend. So I'm going to go over this, and it ties in really well with Lab 8 material, and I'm going to try to give some hints about Lab 8 if you're having any trouble with that. So let's go ahead and dig in. All right, and this says Notebook 10, sorry. That should say Notebook 12, and I do have the title right, Sampling Distributions and the Central Limit Theorem. And I'm going to pause here while you get the notebook open. I just clicked on the link from the course calendar. Go ahead and open that up. And I have also already run the initial block, so why don't you do that? And we'll pick up right here at the top with the variation in samples in just a moment. So what is a sampling distribution? Sampling distribution means that we repeatedly draw samples of the exact same size from some population, okay? Repeated draws of exactly the same size. And it turns out that when I take the means of each of these samples and I produce a histogram of them, I end up with a bell-shaped distribution that's centered around the mean, okay? And here is the most important thing. This is how we estimate values, right? Because we know these sampling distribution means will be centered on the mean of the population, we can use what's going on there as an estimate. Okay, so I want you to think about this because, again, this is what Lab 8 is doing. Lab 8 is talking about these estimates of the mean of the population. Okay, so let's dig right in. And we're back here with the variation in samples. So we have this interesting table called united.csv, which is a bunch of these united flights. How many? Well, there's almost 14,000 rows emitted. So we're talking about 14,000 different flights. And we have the flight number and the destination. I believe H&L is Honolulu. Never having been there, that's on the bucket list, but and the delay column is how many minutes late the flight was, okay? So what we're doing first is we're sampling 100. So we're using the dot sample method, and we're going to take 100 different samples, okay? And then dot column delay, so that's, well, excuse me, then we're taking the sample first, right? And then we're doing dot column. Why? Well, because we need an array. So X is actually an array, which you can see below. Okay, why do we want it as an array? Well, because then we can actually calculate the mean. And the average delay from this sample that we've drawn is about 17 minutes. Now, remember, the dot sample is randomizing things, so that 17.3 minutes is going to change slightly. Now it's just under 13 minutes delay. Okay, and then this is just putting them all together. It's taking the united sample and putting it inside the parentheses of mean, so I can actually, whenever I hit Shift-Enter, it's re-randomizing, selecting a sample, and then taking the mean. Selecting samples, taking the mean. Okay, so here's where the notebook tells us what a sampling distribution is. And I'm going to jump down here. We're talking about the uniform population, the uniform distribution. What's the uniform distribution? The uniform distribution is when all of the bars of the histogram are just about the same height. Okay, well, the uniform distribution is when they're exactly the same height. But what's interesting is when we take this sampling distribution of the uniform population, we actually get a bell shape, right? And I'm intentionally drawing underneath that bell there, and I'll get rid of it. Why? Well, because as we scroll up, let's see how much of this I can get on our screen, on my screen here, right? What's happening? Well, first of all, I want you to know that we start with a shape that's not a bell shape. But then even when we have the smaller sample sizes, we start to see a bell. And what's happening as our sample size gets bigger, you can see the sample size down here, it's increasing. As the sample size gets bigger and bigger, we get a better and better bell shape. It is more symmetric and more closely resembles an actual symmetric bell. Why is this cool? Well, we're going to use these as our estimates. Okay. And so they're centered on the mean. All right, so we're gonna be able to use the center of the bell as an estimate of the mean. And then also I want you to notice the standard deviation. So the standard deviation governs the width of the bell. Okay, so we'll have a much narrower bell when our sample size is large. Okay, sorry, and sorry. So where do we go? Symmetric but non-uniform distribution. All right, so now we're doing the same thing, but check out this crazy distribution, right? This is sort of the anti-bell, right? That we've got this weird thing going on. It's sort of the inverse bell. All right. And still, even though we're drawing from a crazy distribution, you can see as we get higher and higher in sample sizes, we start off with a sample size of 3 and we almost have a bell shape. It's in the first graph, right? But as the sample sizes go up to 15 and then 20 and then 30, we're actually getting some pretty good looking bells at sample size 20 and 30, even though we're drawing from something that is not a bell shape. So that's one of the cool things about the sampling distributions is they always produce bell-shaped data. Why is that important to us? Well, that's a great thing because it makes statistics work. We'll talk more about that in just a second. Okay, so this is a crazy distribution, and this is just showing that no matter how ugly, no matter how weird or funky the original distribution is, that these samples will still turn out bell-shaped. Now, we may need a little larger sample size. Notice that the sample size has gone all the way up to 100 here. Why? Well, because we do have some wonkiness with smaller sample sizes. It isn't quite turning into a bell shape very quickly because this is not bell-shaped, right? But the cool thing is, and the law of large numbers helps us, right? As the sample size gets bigger and bigger and bigger, we're going to get closer and closer and closer to an exact bell shape, okay? And that's the central limit theorem, okay? Now, this one's fun. They start with a normal distribution, and guess what? The sampling distribution comes out bell-shaped. Well, of course, if you start with bell-shaped data, you will end with bell-shaped data. And then what are we seeing? Okay, so this is going to help with Lab 8. What are we seeing? All right, so this is the key. Sample size increased, and we get bell-shaped data, normal distributions. Okay? And this is saying, yeah, when the population is normal to start with, the distribution always looks normal, but the scaling on the x-axis kept changing. Go back and look again. It turns out that the spread, how wide the bell was when you measure the actual x-axis numbers, it actually decreased. And this isn't a coincidence. It's not a trick. So the standard deviations are shrinking. So the standard deviation is sort of like the belt on the histogram, and it's getting cinched tighter, and the standard deviations are getting smaller and smaller as the sample size goes up, right? So as the sample size increases, the standard deviation decreases. It gets smaller and smaller. Why is that good? Because we're trying to estimate in here, and this is a measure of the variation, right? So we can estimate, but there's some variability that happens, so we have to guess sort of at a range of values. But as the standard deviation decreases, right, as our sample size increases, our standard deviation or the variability decreases. And that's really cool. It makes our estimates become more and more accurate for larger sample sizes. And here we go with the large sample sizes saying the same thing that I just drew, right? As the sample size n increases, the average of these different samples will get really close to the population average. And the more you increase n, the closer you get to mu, the population average. Okay. And the central limit theorem says what? Well, so I need a little bit of notation here. This notation where I use a capital N and then parentheses, and then there's two numbers separated by a comma. The first one is the mean. That's why they put mu in here. And then sigma. Sorry, the comma isn't quite where I'd like it to be. What does this notation mean? The capital N means normal, which in statistics, that means bell-shaped. So it's saying, hey, we've got bell-shaped data with the mean of mu and a standard deviation of sigma. So it tells me all the things I need to know about the bell-shaped distribution. Okay. Why does that matter? Because we know that when we do these sampling distributions and we're using large values of n, our sample sizes are big, the sampling distribution is approximately bell-shaped. And as the n gets bigger and bigger, as the sample size gets bigger and bigger, we get more and more bell-shaped, more and more perfectly bell-shaped. And we know that the bell curve will look like this. It'll be centered on the population mean, mu, and it has this standard deviation. Notice that the n is in the denominator, right? The square root of n in the denominator. Why is that important? Because n is our sample size. And this is just basic arithmetic. If you think about it, if I have a fraction and the denominator is getting bigger, then the value of the fraction, the whole thing, is getting smaller and smaller and smaller. And again, that is what's driving this accuracy. The accuracy gets better and better as the standard deviation gets smaller and smaller. Why? Because we have a much narrower bell, right? So if the standard deviation is really small, then we have a bell, and the width of the standard deviation being small, there's just a really small amount of variation around our estimate. We're estimating right in the center of the bell that, hey, the mean's right here. This is mu. This is the population mean. Okay? And again, as the standard deviation is small, then we have just a tiny little bit of variation around the mean. So we get very accurate estimates. And again, the lab is about this, so I wanted to emphasize it and make sure that we talk about it. And then they do make the point that these normal populations don't need the central limit there. Well, okay, if I start with bell-shaped data and I do a sampling distribution, I will end up with bell-shaped data. Okay? So what we've been doing is explained here in this slide, right? That we started with the delay column, and that's the number of minutes of delay for each flight. And negative delays, we saw some of those, refer to flights that arrived early. And we want to know, what is the average delay? Well, we start taking sampling distributions, right? So sampling distribution is repeated samples of the same size. And as that sample size increases, our estimates get more and more accurate. Our estimates become better. All right. And you were seeing that happen in those different charts we took a look at. And so when we're looking at these histograms and on Lab 8, this is what you're looking at. The width is all based on the standard deviation. So I'll put an SD here, right? The standard deviation governs the width of the histogram. And as the histogram gets taller and narrower, thinner, my daughter laughs at me. She says, "Daddy, you're body shaming the histograms." Well, no, I'm really just trying to describe that as this standard deviation gets smaller and smaller, we have a much smaller interval that we're looking at for our estimate of mu. And so the width of the histogram, when we have a really wide histogram, our estimate is not going to be as precise as we'd like it to be, not as accurate, right? We want a really small standard deviation rather than a big standard deviation. A small standard deviation will be a narrower histogram and therefore a more accurate estimate. And the center is our estimate. The center of the sampling distribution is our estimate of the population mean, which we're indicating with a lowercase mu. Okay? And the sample size increase is going to change the accuracy because why? Because as the sample size increases, the standard deviation decreases, right? So as sample size goes up, standard deviation goes down. The increase in sample size leads to a decrease in standard deviation. So then our histogram is very, 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 very narrow, so there's not very much variation in our estimate of this population value mu. Okay. So the law of large numbers, I'm just going to summarize what was there. And you can look in your notebook and see this. So our estimates are pretty close, and we can have a good bit of confidence that they're close. Why? Because the law of large numbers says that if you keep increasing n and n gets large enough, that standard deviation will decrease enough that we'll have a really accurate estimate. And we'll have to wait until after spring break to really define. We can actually make pretty close, pretty accurate, very precise about that, but we'll wait until after spring break. So, and then the means of the sampling distribution have this bell shape. And since they're centered on mu, we can use our histogram of the sampling distribution as an estimate of the population average, and because n is in the denominator, the square root of n is in the denominator, as our sample size increases, we'll get a narrower and narrower bell curve, and therefore a more and more accurate estimate. Okay, so let's jump back in here to the notebook, large random samples. Okay, so we're back in. United is the united.csv table, and we've got flight numbers. And what are they doing here? Well, here they're creating some bins, and then they're graphing the whole delay column in one histogram using these bins that they just created with this NPA range from 20 minutes early. The negative 20 will start at flights that are 20 minutes early and go all the way up until 200 minutes late, or one step before 200 minutes late. So I guess 180 minutes late, but that's 3 hours, by the way. And I hope we don't have to deal with flights like that. And notice that the average is 16.7 minutes, it appears. And now notice that this sample won't match exactly. Why? Because we're taking the average of the whole dang table, all 14,000 flights, right? Here we're taking a sample, size 10. And so the different samples that we take are going to have different averages. Why? And you saw 40 and then 30 and then 11. Why? Well, because every time it's taking a new sample. All right. So now we're going to look at the sample size, okay? And notice that we're going to use, so we're going to take this sample mean 1,000 times, right? And what are we going to see? Sorry, I need to execute this code above it. And we get these sample means forming a bell curve. Okay, now notice that the sample size is 25 here. And we have a bell that's emerging. It's a right skew, right? The tail is much longer over here to the right. But what happens when a sample size goes to 50? Well, we're still seeing a little of that right skew, but notice that we're getting closer and closer. Okay, and when our sample size goes to 4,000, give it a second, it takes it a moment for the 4,000 iterations to be done 1,000 times. And wow, now we've got a really nice bell shape, right? We are getting closer. It's not a perfect bell shape, but it's more symmetric. It's not leaning left or right. It's not skewed left or right. So we're doing better with our estimates. And also notice that while this along the x-axis, this histogram spread out from below 5 to nearly 35. So there's like 30 units there. Here we're only covering from 15 to a little above 18. So let's say 15, 14 to 18 and a half or something. So this histogram is much, much narrower. So now the whole point of this exercise was to see this in action. All right, and then let's go back and finish this up by looking at the actual bell curve. So here's the key thing, right? As n increases, as our sample size increases in these sampling distributions, the standard deviation also decreases, right? I end up with a much narrower bell as the sample size increases, and then my estimate of the average, which is right here on the center, right? I'm trying to estimate what mu is. And my estimate's going to have much less variability as the sample size goes up. And my bell gets narrower and narrower. Okay? So when you're asked about these questions, just remember that sample size and the standard deviation are inversely proportional. Okay? So the accuracy is really related. The variability or the accuracy of our estimates is related to the sample size. And the larger sample sizes are going to lead to smaller standard deviations and therefore much more accurate and precise estimates. So hopefully that will help you on Lab 8, which is due before spring break, and I'll be back after spring break. Have a great spring break, everybody.